Hi everybody, this video will go over section 5 of chapter 4, exponential and logarithmic equations. So let's first review some properties of exponents and logarithms. And this is the first one. If a is positive and not equal to 1, then the following property holds. If a to the x power equals a to the y power, then x is equal to y. Similarly, for all positive values of x, all positive values of y, and all positive base values of a, where a is not equal to 1, then if log base a of x is equal to log base a of y, then x is equal to y. And why is this true? Because both the exponential function and the logarithmic functions are one-to-one functions. So here is our first example. And to deal with this example, we are going to use the power property of logarithms. And that says that the log base a of x raised to the rth power is going to be equal to r times the log base a of x. Okay, so here we have 5 raised to the 2x minus 3 power is equal to 8 raised to the x plus 1 power. So what we want to do is take the log of both sides. Now it doesn't matter which log we use. We can use the common log, we can use a natural log, or we can use the log of any particular base. So let's go ahead and take the common log for each side. So that will give us log of 5 raised to the 2x minus 3 power, and that will be equal to the common log of 8 raised to the x plus 1 power. Now we can apply the power property. So the log of 5 raised to the 2x minus 3 power is going to be 2x minus 3 times the log of 5. And the log of 8x to the first power, or the log of 8 raised to the x plus first power is going to be x plus 1. Times the log of 8. Now that we have the x's out of the exponents, we can actually do some manipulation and solve for x. So we can do some manipulation and we will have 2x log of 5 minus x log 8, and that will be equal to 3x log 3 log 5 plus the log of 8. Okay, and then finishing the simplification, we can factor out the x and divide out the exponents, so we will have that x is equal to 3 log of 5, this is the common log, log base 10, plus the log of 8, divided by 2 log 5 minus 5, there we go, minus log 8. And then if we punch this into our calculator, we will get 6.0624. Since the 10,000th digit is less than 5, this will round to 6.062. And that's pretty much how we solve these problems. Okay, so let's move on to our second one, which is e raised to the 4x power times e raised to the x minus 1 power is equal to 5 times e. Okay, well the very first thing that we can do is we can actually simplify this. Using the product rule of exponents, we can rewrite this as e to the 4x plus x minus 1, which of course will be equal to the 5x minus 1, which will be equal to 5e. We can now go ahead and take the natural log of each side, because remember the natural log of e to the x is just simply x. So here we will have the natural log of e to the 5x minus 1, and that will be equal to the natural log of 5 times e. Alright, well the natural log of e to the 5x minus 1 is just 5x minus 1. The natural log of 5e can be written as the natural log of 5 plus the natural log of e. Of course, the natural log of e is 1, so this can also be written as the natural log of 5 plus 1. Okay, then going ahead and solving for x, we will have that 5x is equal to the natural log of 5 plus 2, and then that x is equal to the natural log of 5 plus 2 divided by 5. And if you punch that into your calculator, you should get 0.7218. Since we went to round to the nearest thousandth, we can look at the tens thousandths place, that's greater than 5. So this will round to 0.722. And this brings us to example 3. Now to solve this problem, we are going to use a change of variables. We have done that with other problems that are quadratic in nature, and this actually is quadratic in nature, or quadratic in form. And what we did was we let u be equal to e to the x. All right, and if we make that substitution, we will have u squared instead of e to the 2x minus 6 times u plus 5 is equal to 0. And of course, this problem is very straightforward to factor. We just want to find factors of 5 that sum to minus 6. And those factors would be minus 1 and minus 5. So we can rewrite this as u minus 1 times u minus 5. And if that's the case, then our solutions will be u is equal to 1 and u equal 5. Well, if u is equal to 1, and then once you've done that, we now want to substitute e sub x for u. So here we will have e sub x is equal to 1, and here we'll see e to the x power, and here we'll have e to the x power is equal to 5. Now, what must x be for e to the x be equal to 1? Well, that is simple or straightforward. X must be equal to 0. For this one, what we can do is we can take the natural log of both sides. And if we do, we will have the natural log of e to the x, which is x, and that will be equal to the natural log of 5. And therefore, our solution set will be 0, comma, the natural log of 5. And this brings us to logarithmic functions. Now, when dealing with logarithmic functions, we must understand that they have a limited domain. Their domain is basically all positive values of x. So if you have a potential solution that you put into a logarithm, if you have a potential solution that will produce a negative value in any argument of the logarithmic function, then that solution must be excluded. Because once again, all arguments of logarithms must have positive values in the original equation. Okay, so let's take a look at this one right here. This one is the log base 4 of the quantity x cubed minus 11 is equal to 2. And we want to find the exact values for x. Now, the one thing that we could do is to raise each of these terms to the 4th power. If we do, we will have 4 raised to the log base 4 of x cubed minus 11, and that will be equal to 4 squared, which is 16. Well, 4 raised to the log base 4 of x cubed minus 11 is just simply x cubed minus 11. X cubed minus 11, and that will be equal to 16. Okay, so now I can subtract 11 add 11 to both sides, and that will give me that x cubed is equal to 27. And if that's the case, well, then x must be equal to 3. And that would be our answer. My kind of problem. Now let's take a look at this one over here. This one is the log of x squared plus 1 plus the log of x is equal to the log of x plus 8. And the first thing we want to do is to deal with this. And we can deal with this using the product rule. And the product rule says that the log of A plus the log of B is equal to the log of A times B. So with that in mind, we can write this as the log of 2x plus 1 times x, or the log of 2x squared plus x, and that will be equal to the log of x plus 8. Once we have this, we can take advantage of this particular property right here, that the log base a of x, if the log base a of x is equal to the log base a of y, then x must be equal to y. And that is what we have here. If these two are equal, and notice here we're using the common log, if these logarithms are equal, then the arguments must be equal. So as a consequence, we have that 2x squared plus x must be equal to x plus 8, which is kind of convenient. That implies that these cancel, and we are left with 2x squared is equal to 8. So what we can do is we can divide both sides by 2. We will have x squared is equal to 4. Taking the square root, we have the proposed solutions that x is equal to 2 and x is equal to minus 2, and these are proposed solutions. When x is equal to 2, we have the log of 5 plus the log of 2, which is perfectly fine, and then we also have the log of 10. Okay, for x is equal to 2. What about x minus 2? In that particular case, we would have the log of negative 2 times negative 2, which is negative 4 plus 1. So that would be the log of negative 3 plus the log of negative 1, negative 2, my apologies. And that will give us the log of 6. Notice that these are negative values, and we cannot have negative values. So these are excluded. These cannot be possible, and therefore x equals 2 must be excluded. As a consequence, the only solution for this particular equation is x equals 2, and the solution set would be 2. Okay, for here we have the log base 2 of 2x minus 5 plus the log base 2 of x minus 3 is equal to 3. Once again, we can take advantage of the product rule. And this says that the log base 2 of 2x minus 5 plus the log base 2 of x minus 3 can be written as the log base 2 of the product of 2x minus 5 times x minus 3, and that will be equal to 3. We can now go ahead and consider the exponential version, or we can now go ahead and consider the equivalent exponential problem, and if we do, we will have that y, or that x, which is 2x minus 5, or the argument of the log, which is 2x minus 5 times x minus 3, must be equal to the base, which is 2, raised to the third power, or raised to the third power, and of course that is equal to 8. We can go ahead and then expand this out, and we will have 2x squared minus 11x plus 15 is equal to 8. We can put this in standard form by subtracting 8 from both sides, and we will have 2x squared minus 11x plus 7. Now notice that there are no factors of 2 times 7 or 14 that would sum to negative 11, so we cannot factor this problem. However, we can solve it using the quadratic formula. You could also solve it using completing the square, but we're going to go ahead and use the quadratic formula. And if you recall, the quadratic formula is that the solutions are x1 and 2 and whatever are going to be equal to negative b plus or minus the square root of b squared minus 4 times a times c, all divided by 2a, where the quadratic equation, where once again a x squared plus bx plus c is equal to 0. So a is equal to 2, b is equal to negative 11, and c is equal to 7. So this means that we will have that our two solutions for x will be negative b, which is positive 11, plus or minus the square root of b squared. B squared is 11 squared, or 121, minus 2 times 4, no, I'm saying, yeah, 2 times 2 would, no, minus 4 times 2, which is 8, times 7, which is 56, and all that will be divided by 2a, or 2 times 2, which is 4. Now it turns out that 121 minus 56 is 65, so we have that x, 1, and 2 are going to be equal to 11 plus or minus the square root of 65 over 4. So we have two solutions. The first one is, or two proposed solutions. 11 plus root 65 over 4. And the next one is 11 minus root 65 over 4. Now it turns out that 11 plus root 65 over 4 is approximately equal to 4.76. And it turns out that 11 minus root 65 over 4 is approximately equal to 0.734. Okay, now we need to exclude those solutions that will cause the argument in both log functions to be negative. Take a look at x sub 2, which is equal to 0.734. 0.734 minus 3, 734 minus 3 is going to be less than 0. Therefore, this argument would be less than 0, and as a consequence, we have to exclude x sub 2. It doesn't matter what happens in this term, although that is also going to produce a negative argument. We still nonetheless need to exclude that. What about x sub 1? Well, it turns out that, that in this particular case, x minus 3 is still greater than 0. And also, 2x minus 5 is also greater than 0. So basically, all these logs will be greater than this, and as a consequence, this solution is acceptable. So the only solution for this particular problem is the only solution set for this particular problem is 11 plus root 65 divided by 4. So just remember, whenever you get your proposed solutions, make sure that it produces positive value arguments and logarithms. Okay, and this brings us to example 7, solving logarithms that are in base e, or natural logarithms. Now notice here we have the natural log of e raised to an exponent. So this is going to be equal to whatever the exponent is, which is the natural log of x, minus the natural log of x minus 4, and that will be equal to the natural log of 5. Here we want to take advantage of the quotient rule. And that states that the natural log of a minus the natural log of b is going to be equal to the natural log of its ratio of a over b. So we can apply that here, and that will give us that the natural log of x over x minus 4 is equal to the natural log of 5. Now we can take advantage of our property of exponents, because if this is true, then it follows that x over x minus 4 is equal to 5. Now notice here we have a rational expression, or a rational expression. As a consequence, we know that this is not defined when x is equal to 4. So let's just hope that x equals to 4 is not one of our solutions. Nonetheless, we can still go ahead and solve this by multiplying both sides by the denominator, and then that will give us x is equal to 5 times x minus 4, or that x is equal to 5x minus 20. That simplifies, we can subtract x from both sides and add 20 to both sides, and that will give us that 4x is equal to 20. Dividing by 4, we have that x is equal to 5. And 5 minus 4 produces a positive number. We have a positive number there. As a consequence, our solution set is 5. Okay, and with that, we can go ahead and summarize what we know about solving exponential and logarithmic equations. The first one is if you have it in the form of a raised to the f of x power being equal to some other constant expression, all we need to do is take the log of both sides, and we have this, and then we can go ahead and solve for f. On the other hand, if it's the log of a function of x being equal to something, we can change that to the equivalent exponential form, which is what we're doing here. And obviously over here is the equivalent logarithmic form. What if you have something? What if you had the log of a of what if you had the log a of f of x equal to log g of x? Well, that implies that f of x is equal to g of x. And what if you have something complicated? Well, at first might be necessary for you to figure out what this is or what that is. And once you've done that, you can apply 1, 2, or 3 to solve the rest of the equation. The only thing which is important is to note that if you are doing a logarithmic, if you're solving a log function, you have to make sure that the proposed solution is in the domain of the particular function. In other words, you have to make sure, or specifically, you have to make sure that the argument of any logarithmic function in the original equation is not negative. And this brings us to our last problem, which is applications, and this has to deal with solving parametric equations. So here we have the parametric equation for cooling, which is basically an exponential decay, and we want to solve this equation for t. So we start off with t equals to t0 plus c raised to the e to the negative k t power. All right, so the first thing we want to do is basically try to get this term, this is the term with the t in it, isolated by itself. And we can do that by subtracting t0 from both sides, and that will give me c e to the negative kt is equal to t minus t0. And so I also went ahead and reversed the order. Now I can divide both sides by c. That will give me e to the negative kt power is going to be equal to t minus t naught divided by c. Now I can take the natural logarithm of both sides, so I'll have a natural logarithm here and a natural logarithm here, and then the natural logarithm of this is nothing more than negative kt, and that'll be equal to the natural log of t minus t naught over c. And then finally I can divide both sides by negative k, and I will have my desired result, which is that t is equal to negative 1 over k times the natural log of t minus t naught over c. And I can put that into MML, and I should be good to go. And that is all I have for this particular section. If you have any questions, please feel free to contact me. This is Bob Boyle, signing off.